Okay, good morning. So, in the previous lecture, we have seen the introduction to the compressible flows, uh, and specifically, we have found that the pressure change is the main cause for compressibility, and compressibility is shown by almost all the fluids, okay, irrespective of their density, viscosity, and other properties. But the only criteria is that if due to compressibility, change in density of a fluid element in a flow field is more than 5%, then we call the flow to be compressible flow. Okay. So now when we study the compressible flows, uh, we are having some sort of flow regimes, flow categorization. For example, in case of incompressible flows, when you study flow over a pipe or flow through a tube, we are having nothing but two kinds of categorizations: laminar flow and turbulent flow. Likewise, when we consider the compressible flow situation in an compressible flow situation also, we can have a number of flow regimes. Okay, so obviously in detail we will be talking about the analysis of each of the flow regime over different kinds of objects. However, over here I would just like to first introduce you the major critical features of almost each flow regime and their terminology, so that this nomenclature we can use in the later lectures. Okay, is this point clear? So first, now we will try to see flow regimes in case of compressible flows. So particularly when we talk about the compressible flows, this compressible flow situation can occur in a large variety of systems. Okay. However, as we have seen from the historical developments also, that particularly the airfoil shape which we see in our aeroplanes, that is considered the very kind of standard geometry for analyzing different compressible flow situations. So what we will try to do over here, whenever we will explain these flow regimes, I will take the help of airfoil structure. Okay, so say I have one airfoil. So this is the typical shape of an airfoil. Okay, so this will be my solid object. Now what will happen, let's say at sufficient distance far from the airfoil I have this flow over here. Okay, so particularly a sufficient distance away from the aerofoil is something which is called as free stream. This is called as free stream, and typically any parameter which we are specifying for free stream, that is actually given with subscript infinity. Okay, so if I have to specify the velocity of all these fluid streams, then I can call that velocity of this free stream is nothing but v infinity, and each of the layer is having the same v infinity velocity. Okay, now let's consider corresponding to this free stream, our speed of sound is a infinity. So we will talk in detail about the speed of sound in subsequent lectures. So over here just consider that a is the symbol for speed of sound, and speed of sound in this free stream fluid is actually a infinity. So corresponding to this, we will be having some Mach number for this. Okay, so Mach number of the free stream will be m infinity. What is Mach number? That I have told you in the previous class. So m infinity will be equal to v infinity divided by a infinity. Okay, is this point clear? Now what we have to do, so Mach number for the free stream is v infinity by a infinity. Okay, so now what will be happening, the way I have defined these parameters for this free stream, likewise I can define these parameters at any location. Okay, so here I will be referring to these parameters v, a and m as the velocity, speed of sound and Mach number corresponding to the free stream. if I am calculating these parameters, say at arbitrary at any location, say at this location, then at this location value of V, A and M I will be calling as nothing but local parameter. Okay. So for example, the Mach number at this location I can say local Mach number. Is this point clear? So the value of Mach number corresponding to the free stream is called as free stream Mach number, and whenever I am calculating this at arbitrary any location, then corresponding to that I can call it as its local Mach number. Okay. Now depending upon the Mach number, actually we will be having different situations. So whenever flow comes over an aerofoil, let me draw some streamline structure. So what I will be finding, one streamline will come like this and then it will follow say path something like this. Then I will be having one streamline like this which will follow some path like this. Likewise, I will be having a number of streamlines, and in certain situation I will be experiencing that the if the gap between the streamlines over here will be almost the same. Okay. And over here you can see I have drawn specifically say 4 streamlines above and 2 streamlines below. So if you talk about the number of streamlines over an aerofoil, there can be infinite number of streamlines, because in each layer wise layer velocity will be different. Okay. And you know what is a streamline? Can you tell me what is the definition of a streamline? What is a streamline? If I take any local location and at this local location if I draw a tangent, so to any streamline if I draw a tangent, that will give me the direction of its velocity at that particular location. Okay. So all like this, because velocity in different layers of the fluid will be different, so we can have a large number of infinite number of streamlines over here. Okay. But just for the representation I am taking a finite number of streamlines over here. Okay. So now this is something flow you can experience something like this. Okay. But let me tell you, this situation you will not be getting all the times. Okay. So this type of streamline patterns may be applicable for one specific kind of the flow regime, and whenever you are actually changing or shifting from one flow regime to other flow regime, then you may have slightly different situation. Okay. Let me also pose one more question to you. Say in this condition I consider that my free stream Mach number m infinity is say less than 1. Now can you tell me what will be the local Mach number over the aerofoil structure? Can you comment on local Mach number? Will it be less than 1 everywhere? If I consider my free stream Mach number as less than 1, then will I be finding Mach number over the complete aerofoil structure always less than 1? Will it be always less than 1? So you may experience that in particularly above the top surface. Above the top surface what is happening? Flow is accelerating. Okay, here flow is actually accelerating. So once the flow is accelerating, you may experience that velocity of flow may become higher. So if velocity of the flow is becoming higher, then you may find some region over here where your Mach number is becoming greater than 1. Okay. So what we will try to do, let's first try to see a flow regime which is called as subsonic flow. Okay. So in case of subsonic flow, what we do, we consider that if our free stream Mach number is less than 0.8 and I have an airfoil structure, I will be experiencing that my local Mach number everywhere is less than 1. Is this one clear? Please respond. So what I am saying is, when my m infinity, okay, free stream Mach number is less than 0.8, corresponding to that, we obtain a situation that at each and every point over the complete span of the aerofoil structure, I will be having everywhere the value of local Mach number less than 1. So when I am able to achieve this type of situation, then we call this flow as nothing but subsonic flow situation. Okay, and the in case of subsonic flow situation, what happens, that this Mach number is so adjusted, 0.8, this value is so adjusted that our local Mach number is actually not going greater than 1. Okay, so if Mach number is going somewhere greater than 1, then flow will not be subsonic. Okay, so subsonic keyword is used corresponding to a Mach number situation less than 1. And as I told you that even if my free stream Mach number is less than 1, then also because of the acceleration in the flow over the top surface of the aerofoil, I can have local Mach number greater than 1. So that's why this free stream Mach number has to be slightly less in comparison to the local Mach number. Is this one clear? So for an airfoil structure, Mach number, free stream Mach number less than 0.8 gives us a situation where local Mach number will not go beyond 1. Okay, so this type of flow situation is called as subsonic flow situation. Okay, then comes the next flow situation. Another important feature of this type of flow situation is that if you experience this, your streamline has started bending sufficiently far from the nose of the airfoil. Okay, so you see this is the starting edge, leading edge of the airfoil, but if you see the bending of the streamline, that is happening at sufficiently large distance or sufficiently far from the leading edge of the airfoil. Okay, so here there is a smooth transition in streamline pattern. Okay, now next type of flow is called as transonic flow. So what happens in case of transonic flow? In case of transonic flow, you will be finding that particularly this type of flow regime is actually categorized into two categories of free stream Mach number. So this is the first category I am showing to you. So when your free stream Mach number is from 0.8 to 1.0. Okay, so when your free stream Mach number is greater than equal to 0.8 and less than 1, in that situation you will find that in this particular region, which I am showing with dashed line over here, in this particular pocket you will be finding that local Mach number is greater than 1. So this Mach number over here is greater than 1. Okay, so in this situation we will not be having everywhere Mach number less than 1. So because of the acceleration of the fluid over the top surface of the airfoil, in some local pocket we will be finding that our Mach number is greater than 1. Okay, and particularly if you see behind this, I will be finding immediately behind this pocket, I will be finding the occurrence of a shock wave. So here I will be having a shock wave. So basically what is shock wave, that subsequently we will try to see, but one important point is at the occurrence of the shock wave we will be having sudden changes in the properties. Okay, so there will be discontinuities in the flow field and we will be having sudden changes in its properties. Okay, up to this point is it clear? Now another situation also which comes in the origin of transonic flow, that is, if this is my airfoil structure, okay, and over this airfoil structure once again the flow is happening in a similar way, but only one difference is that, what is the difference? The difference is that Mach number is now from 1 to 1.2. Okay, so now we have Mach number from 1 to 1.2. Okay, so in this situation what happens? In this situation we find the occurrence of two shock waves. Okay, so one shock wave I will be having somewhere over here, which is called as bow shock wave, and one shock wave I will be finding at the trailing edge of the aerofoil, which is called as trailing edge shock wave. Okay, so here I have wrongly drawn these streamlines. Let me remove this, particularly near the shock wave, because there will not be smooth transition in streamlines. Okay, so streamlines will be having some discontinuity. So what will happen now in this region, particularly near the nose, we will be finding that here Mach number is less than 1, and in the remaining region we have then Mach number greater than 1. So what has happened, initially whenever the free stream is approaching, so free stream is almost, streamlines are parallel and these are almost normal to this bow shock wave. Okay, however at this point suddenly Mach number will become less than 1, so there will be sudden transition in streamline pattern, sudden transition in properties. Okay, and in this particular pocket Mach number will be less than 1, and after the flow has gone beyond this pocket, then Mach number will once again become greater than 1, and finally we will also experiencing one more sudden transition in the properties, one more discontinuity. So that is called as actually trailing edge shock wave. Okay, so this type of flow situation is called as transonic flow situation. Fine. Then we have next, that is called as supersonic flow. Okay, so let's consider I have a wedge shaped geometry. So whenever we will be considering, we will be finding the supersonic kind of jets, then you will be finding the tip of the actually our body is more sharp. Okay, so that's why I'm considering this over here as the wedge like structure. So say I have a wedge like structure, and over this wedge like structure flow is happening. Okay, so if our Mach number is, free stream Mach number is greater than 1.2, then we will be finding that there will be occurrence of a shock wave at the tip of this wedge. Okay, and this type of shock wave is called as oblique shock wave. Okay, so this is the representation of a typical oblique shock wave. Okay, and what I will be finding, when the flow is happening, initially streamlines will be something like this. Okay, free stream streamlines, completely horizontal, and then you will be finding a sudden change in its angle. So in case of subsonic flow, what was happening, subsonic or transonic flow, the streamline was showing a smooth transition, and that transition was also occurring at sufficient before reaching to actually the tip of the object. Okay, however over here what is happening, up to the shock wave flow is actually completely horizontal. Okay, and once it has reached the shock wave, then there is sudden change in the path of the streamline. So whatever this far alarming situation was there, like in case of subsonic flow, so that earlier only it was alarming that it has to change the path. So that is not happening over here. Okay. So this type of flow situation is called as actually supersonic flow situation. Okay. Then comes another situation which is called as hypersonic flow. So in case of hypersonic flows, what happens? Once again, we are having this wedge shaped structure. Okay. And in this wedge shaped structure, I will be having the occurrence of a shock wave. But this shock wave will be very much adjacent to the surface of the object. Okay. So say here, this shock wave is almost attached to the surface. And below this shock wave, what I will be having? Below this shock wave, whatever fluid I will be having, that is something which is called as shock layer. It is very thin. Okay. So shock wave is almost attached to the body. So, and this particular region is called as shock layer. Okay. This situation typically comes when Mach number is greater than, free stream Mach number is greater than 5. Okay. So this is once again a debatable criteria, that always hypersonic flow occurs at Mach number greater than 5 or not. So typical answer is that, okay, thumb rule is it occurs somewhere close to 5 or 6, but this is not always true. So say the more generic criteria is that basically the transition from supersonic to hypersonic flow is particularly the function of shape of the body and what is the free stream density of the fluid medium. So that is the more robust thing. Okay, depending upon that it actually changes. Now once we have exceeded the critical limit of supersonic flow, like Mach number greater than 1.2, after that we experience that the increase in pressure, temperature and density is actually very high, almost an exponential increase with increase of the velocity, okay, or free stream Mach number. So particularly for hypersonic flows, we obtain a situation where in these shock layer regions temperature is very high, temperature is extremely high. Okay. So say I can say that as high as of the order of about 4000 kelvins. So temperature will be very high. Okay. So in this situation, what will happen? Whatever the fluid you are having, which is encapsulated in this shock layer, that particular fluid medium will be basically ionizing. If that is ionizing, then we will be having occurrence of chemical reactions over here. Okay. So due to these things, here actually the study of or analysis of hypersonic flows is extremely challenging. Okay, because temperature is very high, because of which the immediate surrounding medium, that will be ionizing, and we may have even lot of chemical reactions over here which will be actually governing the complete dynamics. Okay, so this is the reason that in case of hypersonic flows actually we can have complex analysis, and particularly in this particular course also we will not go deeper into the study of hypersonic flows. Okay, so from surface level only we will try to see certain aspects. Okay, but we will not go much deeper into the hypersonic flow situations. Mainly hypersonic flow situations you can see in rocket engines. So when the hot gases are coming out of the nozzle of a rocket engine, there you can find out the occurrence of hypersonic flows. If you are having a space ship, okay, spacecraft, and that is coming from the space, once it enters the atmosphere, corresponding to that point also we experience the very high Mach numbers and a situation of hypersonic flows. Okay, once a spacecraft enters the atmosphere. Okay, now let's try to see so this is all about the flow regimes. Okay, so 4 different types of flow regimes we experience in case of compressible flow. Now we will be talking about specifically the gases. Okay, so in case of fluids, already we have seen that liquids are having less compressibility. Okay, more compressibility is shown by gases. So majority of the compressible flow analysis we will be presenting for gases. Okay, whenever we consider a gas, we know that at certain conditions gases can be idealized as ideal gas behavior, or we also call it as perfect gas behavior or thermally perfect gas behavior. Whereas if we go in certain range of parameters, then gas behavior cannot be completely analyzed as an perfect gas. Okay, but in majority of the situations over here which we will be dealing, we can consider the gas to be a perfect gas. Okay, so let's try to see first some of the important equations of a perfect gas and how these will be useful for a compressible flow situation. Okay, so can you tell me what are the two main important characteristics of a perfect gas or an ideal gas? More generally, we also say many times ideal gas. What are the two important characteristics? Okay, temperature and pressure is something fine. So that is what we do in ideal gas equation. We try to relate the parameters in the form of an equation. But in order for a gas to show the ideal gas behavior, what should be there? Density should be less. The measure point is intermolecular forces should be weak or strong? Weak. So there should not be any intermolecular interactions. That is the measure point. Okay. So if we have a gas with weak intermolecular forces, for that particular gas we can write PV equal to N R bar into T, where P is pressure of the gas, V is volume of the gas, T is its temperature, N is number of moles of a gas. What is R bar? R bar is known as universal gas constant. So all of you please revisit your concepts of thermodynamics. Universal gas constant. Okay. Now in case of number of moles, we can specify it as nothing but mass of a given mass of the gas divided by its molecular mass. Okay, so if I do this replacement, I will be finding P into V equal to small m by capital M into R bar T. Now this R bar by molecular mass, this we call as R and it is called as characteristic. Why I am calling it as characteristic gas constant? Yes, it is having different values for different gases because this is universal gas constant divided by molecular mass. Okay, and universal gas constant R bar is having value 8.314 kilojoule per kg mole Kelvin. What is kg mole? Kilogram moles is the unit of number of moles. Okay, unit for that is nothing but the kilogram mole. Okay, now this, if you consider air, what is the molecular mass of air? 29. Okay, if you consider air, for air what you will be finding? R of air is equal to R bar by its molecular mass, and that will be coming out to be 0.287 kilojoule per kg Kelvin. Okay, so now if you see, if R bar by M you write as R, then you will be finding that P into V equal to MRT. Okay, now if you divide throughout by M, then you will be finding P into V by M is specific volume equal to RT. Okay, and from here, this V specific volume, if you take on the right hand side, you will be finding P equal to rho RT. So this is one important relation which represents the variation of density as function of pressure and temperature of a gas. Okay, so this is one very important relation which is useful in the compressible flow analysis once we consider a gaseous medium to be an ideal gas. Okay. Then another interesting point is, if I take this original equation in terms of number of moles, PV equal to nRT, n R bar T. Okay. Now if I divide this equation by volume, then what I will be getting? P equal to N by V R bar T. What is N by V? Number of moles of a gas per unit its volume, per unit volume. This is called as concentration. Say if you have mixture of gases in this room, okay, and if you consider the volume of that mixture, and if you know the number of moles of one gas in that mixture, then you can calculate the correspondingly concentration of that particular gas in a mixture. Okay, is this point clear? So N by V is nothing but the concentration. Another interesting fact is that, so I can write this as, say, P is equal to C into R bar T. Another interesting fact is that the number of moles of a given mass of a gas is same for all different kinds of gases. Why? What is number of moles? Mass upon molecular mass. Okay. So a gas comprises of large number of molecules in a continuum level. If you consider, say, 1 kg of a gas, that 1 kg of a gas is actually formed by a large number of molecules of that particular gas. Okay. So if I know the molecular mass, then total mass of the gas will be nothing but number of molecules it is having, okay, multiplied with mass of each molecule. Is this point clear? So now for different gas molecules, molecular mass will be different. Okay, and ratio of this, because this ratio, a given mass is composed by a n number of molecules, as this is coming in the ratio given mass upon molecular mass. That's why number of moles for a particular gas will for different gases will be a fixed number. Have you got this point, what I am saying over here? Is this point clear? The point is, say you say that 1 kg of a gas, okay, if you consider air is having molecular mass, say 29, okay, so for 29 kg, now if you have, say, how many number of moles that is composing this mass, 29 into n1 number of moles is forming 1 kg. Okay. Now if you say take another gas, carbon dioxide, what will happen? How much is the molecular mass? 44 into n2 number of molecules will form 1 kg. Okay. So basically this mass of 1 kg is formed by number of molecules, number of moles. Will this N1 and N2 will be same? Can it be same? Please tell me. If in place of this I write 1 kilogram mole, will it be same? What is Avogadro's number? As per this number, 1 kilogram mole of a gas contains 26 or say molecules. 1 kilogram mole for any gas is always a fixed quantity. Okay, why it is a fixed quantity? This is basic physics question. So, sorry, basic physics or chemistry question. I will not tell over here. You try to find it. Okay. Why this is a fixed quantity always? Okay, you try to find it by your own. At the moment, say I have this Na. What I will do now? I will multiply and divide both sides of this equation by Na. Okay. So, what I will get? P into what I was having in the previous slide. P is equal to Na times C divided by Na into R bar T. Okay. So what I have done in the previous equation, which is involving concentration, I have multiplied and divided by Na. Okay. So what is this Na into C? Na is number of molecules and Ca is concentration of a gas. What does this will form? This will give us the number density. Okay, number of molecules in unit volume of a gas. Is this point clear? So this will become P equal to N, where N is called as number density of a gas. And here I will be getting R bar by N A. And T. What is R bar by Na? What is R bar by Na? Have you heard of any parameter K? What is this K? Boltzmann constant. Okay, K is universal gas constant per unit Avogadro's number is something which is called as Boltzmann constant. And this Boltzmann constant is having magnitude how much? Somewhere close to 1.38 into 10 to power 23 joules per Kelvin. This is the value of Boltzmann constant. So this is also one important equation, and this particular equation is actually needed when we are having what type of flow situation? Hypersonic flow situation. Why this is important for hypersonic flow? Because in case of hypersonic flow, our concentration of the gases will keep on changing. We will be having mixture of gases. Okay, if you have certain molecules of certain gas, that will ionize at very high temperatures, and there will be occurrence of the chemical reactions. Due to these chemical reactions, we will be finding that concentration of each gas is actually changing during the flow. Okay, so that's why we are considering, if concentration is changing, it means number of molecules are changing. How number of molecules are changing? Older molecules are breaking, reacting with the other reactant species and forming the new molecules. Okay, that is what happens in a chemical reaction. If you are having, say, methane CH4, which is reacting with oxygen, what it will do? It will form CO2, and so if you see, the number density of methane molecule that has decreased, and number density of carbon dioxide and water vapor molecule has increased. So it means if you are having a reacting situation, then number density of the molecules will be actually changing. So once the number density of the molecules is changing, then we will try to consider this form of actually ideal gas equation for our analysis. Is this one clear? Because in the previous form, what we are considering, we are only considering the density of the complete mixture. So here number density is actually not changing, species are non-reacting. Okay, so these are the very fundamental concepts, nothing but we should be able to interpret what equation is actually telling us. Inferences should be made. Okay, is this point clear? Now when we do this ideal gas analysis, so for majority of the flow situations, particularly we will be finding, if you see compressibility chart, let me explain that as well. Do you know about compressibility chart? Have you not studied basic thermodynamics? We call compressibility factor, say Z equal to PV by RT. If value of Z is equal to 1, then it means our behavior is ideal gas or thermally perfect gas. Okay. If our value of Z is greater than or less than 1, then we call the behavior as a real gas behavior. Okay. So compressibility chart is a chart which plots Z along ordinate and pressure along abscissa, and over this chart we plot the different temperature lines. Okay, so say for a substance, this is my liquid vapor dome and this is the critical point. Is this one clear? So for a substance, I will be finding that, say this is the value of Z equal to 1. At very low pressure, I will be always having my Z value equal to 1. And whenever I go towards the high pressures, I will be finding value of Z becomes less than 1, and then at very high pressures once again it becomes greater than 1. So this is, say, at some temperature T1. Now if I change the temperature to T2, then I will find once again the line will be initially something like this, then it will go down, and then once again it will become higher. And at very high temperatures, I will get a situation where after this point line will keep on only increasing. Is this one clear? So what happens? Why in this region the value of Z is less than 1, and why over here value of Z is greater than 1, and why in this region value of Z is equal to 1? At very low pressures, density of gas will be less. If density of gas is less, then molecules will be far away from each other. If molecules are sufficiently away from each other, these will not be having the intermolecular attractions. So intermolecular forces are weak. If you keep on increasing the pressure at a given temperature, So increasing the pressure, it means you are increasing the density of the gas and molecules are coming closer to each other. Once molecules has come in the vicinity of each other, then they will try to attract each other. So in this zone, there will be attraction forces between the molecules. Once these are having attraction forces corresponding to a given pressure, a gas without interactions, whatever volume it would occupy, with interactions it will occupy, even with attractive interactions it will occupy what kind of volume? Lesser or more? Lesser. Please listen carefully what I am saying. I am saying that if say I am increasing the pressure, so increasing the pressure is obviously bringing the molecules closer and their volume is decreasing. Gas volume is actually decreasing. Okay. Now, if at a certain pressure our molecular locations are such that intermolecular attraction forces are becoming prominent. If intermolecular attraction forces are becoming prominent, then what will happen? Sorry? Attraction will be more. If more attraction is there, that will bring the molecules more close to each other in comparison to a perfect gas where attractions are negligible. So that is the reason that in this zone a gas with interactions will occupy less volume in comparison to an ideal gas. That is the reason that in this zone I am having value of Z as less than 1. When you go keep on increasing the pressure, you will get a situation where pressure is so high that molecules are very close to each other. Once molecules are very close to each other, in place of attraction forces, these will show the repulsive forces. There is some critical distance. If you bring molecules closer to the critical distance, then in place of attractive forces, you will experience the repulsive forces. Okay, so this is the zone where molecules are so close that they are experiencing nothing but the repulsive forces. Okay, so if you consider ideal gas behavior, which is without the intermolecular forces, that will occupy less volume in this zone, whereas a real gas will occupy more volume. So this is the reason for having value of Z greater than 1 in this region. Is this point clear? So it means that one interesting fact we can see that at very low pressure, almost at all the temperatures, gases behaves as ideal gas. Another point is that at very high temperatures also and moderate pressures. So this reason you can say that this is the reason of a moderate pressure and very high temperature. Because in this moderate pressure region, if you consider low temperature, then you are getting Z less than 1. But here Z is very close to 1. So it means in moderate pressure and high temperature also gas behaves as an ideal gas. But if you go to very high pressures, then irrespective of the temperature, gas will be showing actually the real gas behavior. Okay, is this point clear? Now you understand what is the applicability, in what range of pressure or temperature there is applicability of ideal gas behavior, thermally perfect gas behavior, and in what zone there is applicability of real gas behavior. Okay. Now comes important point. If a gas is not an ideal gas, then obviously you have to go for some other equation of state. Okay. So then we go for some, say, one equation of state. Famous equation of state is called as van der Waals equation of state, where we are having P plus AY V square into V minus B equal to RT. So this is van der Waals equation of state. Okay. So here this first term actually accounts for nothing but the intermolecular forces. This accounts for intermolecular forces. And another important point which we consider in ideal gas behavior is that volume of the gas molecule is negligible in comparison to the overall volume of the system. Okay, so here this term is to account for the volume of the molecule. Okay, is this one clear? In majority of the compressible flow analysis, we will be finding the high enough temperatures and moderate pressure. That's why majority of the compressible flow analysis can be performed by idealizing the gas behavior, by considering a thermally perfect gas. Is this point clear? So I can say that a thermally perfect gas or ideal gas will be applicable for moderate pressures and high temperatures, and at very low pressures at all temperatures. So this is something which I initially didn't thought that I have to teach this, because I expect that you people should know this from the concepts of thermodynamics. Okay, so all of you, please, I suggest all of you to revise the concepts of thermodynamics. Okay, another interesting point is that along with the thermally perfect gas, we also call one more point calorically perfect gas. Now, can you tell me what do we mean by calorically perfect gas? Can any one of you tell me what is calorically perfect gas? A gas for which values of its specific heat. What are the specific heats? Cp and Cv. A gas for which values of its specific heats can be considered constant, that is called as calorically perfect gas. Okay, majority of the gases at temperature less than or equal to 1000 Kelvin can be considered as calorically perfect gases, because their Cp and Cv can be considered constant with reasonable accuracy. Okay, however, if you go from 1000 degrees to somewhere 25,000 Kelvin to somewhere around 2500 Kelvins, then uh, the dependence of temperature comes on Cv and Cv. So these becomes strong function of temperature. So in this particular zone, the molecular vibrations become so important that this changes the values of Cp and Cv. So that is why this becomes strong function of temperature. If you go at temperature greater than 2500 Kelvin, then you will be experiencing that O2 molecules will dissociate. If O2 molecules are dissociating, then obviously these will participate in the reaction. Okay, so this you can say a typical situation for a hypersonic flow. Okay, and at temperature greater than equal to 4000 kelvins, you will experience that N2 molecules will dissociate. Okay, so here we will be having even dissociation of the N2 molecule. So you can say that up to a temperature of 1000 Kelvin in a flow field, you can take with reasonable accuracy the assumption of a calorically perfect gas. However, if your temperature is greater than 1000, then you have to consider the dependence of temperature on variation of Cp and Cv, and when temperatures are becoming more than 2500 Kelvin, then obviously the reactions are to be considered, and you cannot consider the gas to be a perfect gas at all. Okay, so now I will stop at this point. I suggest all of you please recapitulate your concepts of basic thermodynamics. Okay, these will be very essential throughout the complete course. In the subsequent lectures also, I will take revision of concepts of thermodynamics, but that will be just brief recapitulation. For your detailed understanding, please revisit to the take any standard textbook of thermodynamics and have a detailed reading of the subject. Okay, now we will stop. If you have any